Afterload is another factor that affects stroke volume and cardiac output. The afterload is the load or force on the ventricle during contraction, and it can be considered to be the force or pressure that the ventricle has to overcome in order to eject blood. A precise measure of ventricular afterload involves measuring the ventricular wall stress, since this is what the cardiac myocytes have to work against during pressure development and shortening. Wall stress, and therefore afterload, can be estimated using the law of Laplace, which states that the wall stress equals the ventricular pressure times the ventricular chamber radius divided by 2 times the wall thickness. Since ventricular radius and wall thickness remain relatively constant, the pressure is the primary variable that determines changes in wall stress or afterload. The left ventricle ejects blood through the aortic valve and against the high pressure of the systemic circulation. So you can also think of afterload as being proportional to the pressure of the systemic circulation or the systemic vascular resistance. Increasing afterload leads to a decrease in the volume of blood ejected by the ventricle or the stroke volume. This graph shows a force velocity relationship in an isolated cardiac muscle fiber. So we see the relationship between the afterload and how much and how fast that cardiac myocyte shortens during contraction. And this curve shows that the speed of cardiac muscle contraction depends on the load that has to be moved. Or in other words, the velocity of cardiac muscle shortening depends on the force or load against which the muscle is contracting, or the afterload. The maximum velocity of shortening, or this Vmax, occurs when there's no force or no load for the ventricular myocyte to work against. In other words, this is when the afterload is 0. As increased force or load is placed on that ventricular myocyte, it causes it to shorten less and more slowly. And this occurs because the greater force or load opposing the contraction, or the afterload, the slower the rate of the actin-myosin cross-bridge cycling, and therefore the lower the velocity of sarcomere and muscle fiber shortening. And it's this amount and velocity of cardiac muscle fiber shortening that's directly related to stroke volume in an intact heart. So at a very low afterload, the sarcomeres become very short very quickly, which allows a large volume of blood to be ejected from the ventricle during systole and a large stroke volume. Then as the afterload increases, the sarcomeres are able to shorten less and they shorten more slowly, so less volume can be ejected from the ventricle during the limited time in the cardiac cycle for systole, and the result is a decreased stroke volume. On the pressure volume loop, preload is easily identified as a single point at the end of ventricular filling. Afterload, on the other hand, isn't a single point, but instead it's the integrated pressure throughout this entire period of systolic ejection. So afterload is the force that the ventricle has to contract against and overcome to expel blood. Since the pressure Afterload's the force the ventricle has to contract against and overcome in order to expel blood. And since pressure is an important component of this force, as defined by the law of Laplace, afterload can be considered to be proportional to the aortic systolic pressure, which is represented by the left ventricular systolic pressure on this pressure volume loop. And the reason for this is that the aortic systolic pressure can be considered to be equivalent to the ventricular systolic pressure indicated here, because during this period that aortic valve is open and the pressure between the aorta and the ventricle is equalized. Now let's look at the effect of changes in afterload to the pressure volume loop. In this blue reference heartbeat with a standard afterload, we see that the ventricle contracts and generates a large amount of pressure during isovolumetric contraction, which eventually causes the aortic valve to open, and the remainder of that contraction is used for ejection. Then the ventricle begins to relax, the pressure drops below the pressure in the aorta, causing the aortic valve to close, and the ventricle continues relaxation with all the valves closed during this isovolumetric relaxation. until the point where the ventricular pressure drops below the pressure in the atrium. Then the mitral valve opens and ventricular filling can occur again. Let's see what happens when we increase the afterload or the aortic pressure. Ventricular filling occurs as usual and preload's not affected, at least initially, so the left ventricular end diastolic volume and pressure is the same as in the normal beat. Contraction begins, and because of the increased afterload, there's increased maximum pressure reached during this period of isovolumetric contraction. Then, once the pressure in the ventricle is finally higher than the pressure in the aortic valve opens, and the remainder of that contraction is used for ejection. However, because of the increased afterload, the muscle fibers are shortening more slowly, and since systole occurs only for a limited time during the cardiac cycle, with a decreased amount of velocity of ventricular myocyte shortening, there's also a decreased velocity of ejection, and less blood volume can be expelled during this ejection. And the result is an increased left ventricular and systolic volume. Once the sarcomeres have shortened as much as they're able to and the ventricle begins to relax, the pressure in the ventricle drops below the pressure in the aorta, causing the aortic valve to close. The ventricle continues to relax during isovolumetric relaxation until the pressure in the ventricle drops below the pressure in the atrium, when the mitral valve opens and filling can begin again. So the stroke volume is the end diastolic volume minus the end systolic volume, and it's the width of the pressure volume loop. So with this increased afterload, there is an increased end systolic volume, so the pressure volume loop is more narrow and the stroke volume is decreased. It's important to note that this red pressure volume loop shows the first cycle or the first heartbeat after an increase in afterload, and this shows the most drastic decrease in stroke volume. During subsequent beats, since the end systolic volume is increased, the ventricle fills more during diastole and results in an increased preload. And because of that Frank-Starling mechanism, this increased preload causes an increased force of contraction and brings the stroke volume back up into a more normal range, even with that increased afterload. The relationship between preload and afterload can also be seen on this cardiac performance curve, which is also known as the Frank-Starling curve. Remember that based on that Frank-Starling relationship, the volume of blood the ventricle pumps out, or the stroke volume, depends on the volume in the chamber at the end of diastole, or the preload. This is because the force of contraction is proportional to the length of the ventricular myocyte at the end of diastole. So increasing the volume of blood in the left ventricle at the end of diastole stretches the ventricular myocytes, which allows the actin and myosin filaments to align, causing more cross bridges to form, increasing the force of contraction and therefore the stroke volume. This black line is a reference and it shows a normal afterload. But if the afterload was decreased, then the stroke volume would increase. And this is because the ventricle would be pumping against a lower pressure in the aorta, so the myocytes could shorten further and faster, and the curve would shift up and to the left. So for the same preload value, there's now an increased stroke volume because there's less force or pressure that's opposing that ejection. If the afterload was increased, on the other hand, and the ventricle was pumping against a higher pressure, the ventricular myocytes would shorten less and more slowly, shifting the curve down and to the right. So for that same preload value, there's a decreased stroke volume, and that's because there's more opposition to ejection. So in addition, that Frank-Starling mechanism still applies regardless of the afterload. So increasing preload causes an increased stroke volume at any given afterload. So this is used as a compensatory mechanism. This means that if afterload is increased and stroke volume is therefore decreased, preload can be increased to bring the stroke volume back into that physiologic range. And if afterload is decreased and stroke volume is therefore increased, preload can be decreased to bring the stroke volume back down. There are a few factors that are important in determining afterload. As we said before, afterload can be considered to be proportional to the systemic vascular resistance. That systemic vascular resistance is the total resistance in the entire systemic vascular system, and it's a major determinant of aortic pressure and therefore the afterload of the left heart. The systemic vascular resistance can be estimated by the systolic blood pressure, and vasoconstriction would increase the systemic vascular resistance and therefore the afterload, while vasodilation would decrease that resistance and the afterload. So the left heart ejects blood through the aortic valve against the high pressure of the systemic circulation. That's the systemic vascular resistance, while the right heart ejects blood through the pulmonic valve against the lower pressure of the pulmonary circulation, or the pulmonary vascular resistance. The compliance of the aorta, or its ability to distend, is another determinant of afterload. So with aging, the large arteries become less compliant because there are changes in the collagen and elastin in the vessel walls. And that decrease in compliance results in an increase in systemic vascular resistance and therefore afterload. So because of the decreased compliance, the stiff aorta can't stretch during ejection and the systolic pressure rises higher than normal, resulting in an increased afterload. The aortic valve can also introduce resistance to the system. Normally, the aortic valve opens fully during ejection and doesn't impose any resistance. But when there's narrowing of that aortic valve opening, as is the case in aortic stenosis, for example, afterload is increased because resistance has been added at the level of the aortic valve.